All applications have to deal with data in one way or another, and most of them need data that persists from one execution of the application to the next. In this video, we summarize some of the most challenging aspects of designing data-driven applications. Choosing the right option for persistent data storage depends on various factors including data structure, access patterns, scalability requirements, transaction needs, and so on. The main choices are between file system storage or a database, and whether the data is stored locally or on a remote server. File system storage is a good choice for managing large, unstructured data, such as images, videos, documents, and logs. It's particularly useful for applications requiring straightforward and scalable file access, like media streaming platforms and backup solutions. However, it lacks advanced querying capabilities and is less suitable for structured data that requires frequent updates, complex queries, or transactional integrity. Databases, on the other hand, are ideal for managing complex, structured data and enabling efficient querying and transactional operations that are not found in file system storage. There are two main categories of database: relational and NoSQL. Relational databases are powerful and efficient systems designed for managing structured data and complex relationships, but they do have some limitations. A primary concern is their scalability, typically achieved through vertical scaling by upgrading hardware, which can quickly become costly and impractical. They also require strict schemas, making them less adaptable to evolving application requirements, especially with diverse or rapidly changing data. Additionally, relational databases may experience performance issues with large datasets and complex queries involving multiple table joins. It's important to understand some key terms for relational databases. A schema defines your database structure, including tables, fields, relationships, and constraints. Tables organize data into rows and columns representing specific entities. A primary key is a unique identifier that ensures each table row is distinct. A foreign key connects tables by referencing a primary key in another table. Normalization is a procedure that organizes data to reduce redundancy. The ACID properties are design constraints on relational database engines that ensure transactions are atomic, consistent, isolated, and durable for data integrity. The standard way of representing a relational structure is with an entity relationship diagram, or ERD. The example shows how tables are represented by rectangles and relationships by lines linking the tables. This ERD uses the crow's feet convention, which is common in tools such as StarUML and Mermaid. NoSQL databases offer significant flexibility and scalability but have their own drawbacks. One major challenge is the absence of a standard query language like SQL, making learning and integration more complex. NoSQL databases often use eventual consistency, meaning there could be brief periods when data isn't fully synchronized, posing challenges for applications needing real-time accuracy. Additionally, these databases may compromise on transactional reliability, impacting applications where data integrity is paramount. NoSQL databases are often categorized according to their fundamental data structure. Document stores are databases storing data in flexible documents such as JSON. Key-value stores are simple databases storing pairs of keys and values for rapid access. Column family stores organize data in columns for efficient querying. Graph databases manage interconnected data through nodes, edges, and properties. NoSQL databases often implement sharding, an approach to distributing data across multiple servers for enhanced performance and scalability. When developing software, database requirements often change as the application evolves. This leads us to the concept of database migrations. Migration is a structured approach to modifying your database schema over time. Common changes include adding new tables or columns, altering existing columns, or deleting outdated structures. A key challenge with migrations is maintaining consistency across different parallel environments, such as development, testing, and production. Each environment may be running different versions of the database schema simultaneously. Without careful management, migrations can result in data conflicts, data loss, or inconsistencies. Therefore, it's critical to implement robust version control, use migration tools effectively, and follow clearly defined migration procedures to keep your data safe and your schema accurate across all environments. The acronym CRUD stands for Create, Read, Update, and Delete. Implementing these basic operations is typically a foundational step for application development. Solid CRUD functionality prepares the ground for the development of more sophisticated application features, streamlining development and testing, while ensuring maintainability and scalability. An Object-Relational Mapper, or ORM, is a software layer that simplifies database interactions by allowing developers to work with data in an object-oriented way, rather than writing raw SQL queries. It acts as a bridge between relational databases and object-oriented programming languages, automating the process of mapping data between tables and objects. This example illustrates the use of C# with Microsoft's Entity Framework. The time dimension adds another complexity to database design. Managing temporal data can be challenging, as visualization and appropriate structuring can be difficult. Without careful consideration, you may over-engineer database structures unnecessarily. Clearly distinguishing between static data, which rarely changes, and dynamic data, which changes frequently, helps maintain simplicity and efficiency. Finally, let's consider user interface design for data-driven applications. Typical UI components include list pages, which provide structured views reflecting the underlying database schema for easy searching, filtering, and sorting. Single record views, which offer detailed views aligned closely to the database structure for reviewing or editing individual records. And master detail layouts, which combine lists and detailed views to represent related data clearly and effectively. The relationship between these common page types and the underlying database structures is obvious. However, it's essential to recognize that strictly reflecting database structures in the UI may not always be the most intuitive for users. Sometimes, data needs to be presented differently to match user expectations or workflows. This is where the developer's skill comes into play, balancing an efficient, maintainable implementation with a design that enhances usability and user experience. In summary, while some of these concepts seem straightforward, implementing them effectively can lead to complex challenges and dilemmas. Developing proficiency in designing data-driven applications takes time, effort, and practical experience. It's a journey of continuous learning, and the deeper your experience becomes, the better you'll navigate the intricate decisions essential for successful application development.